Okay, so double checking, it says pause recording. So that means I am recording. I thought I had more. So the first one is I gave you a transfer function. And I gave you some coefficients. And I tell you that it's a second order high pass filter, but I also say that it's Butterworth. Now, Butterworth filters, we're going to get into why later, but they have complex poles, right? If I said a second order high pass filter that was critically damped, we'd have a repeated real pole. And if I said second order high pass filter that was overdamped, I'd say there was two different real poles. But the Butterworth means they're complex. It's almost like a definition. Again, why that's so, we can talk about later. And yeah, there is like a kind of like a generic way to write this, that this constant would be 2 times the damping coefficient. Again, this is just, we're almost about to get into that. Omega naught S plus omega naught squared. And really, for this kind of Butterworth filters, where we have the possible choices band, low, and high, right? It's all in the numerator. So the bandpass is S omega naught. The low is omega naught squared, and the high is just S squared. Notch, it's the sum of some, it's this, the notch is the sum of the high and the low. Okay. So really, the denominator is the same thing. And the thing is once you get the circuit done, all you have to do is change where you're taking things and you get kind of the same filter for, I guess, effectively for free almost. So let's just do this in the shorthand way. right? You wouldn't have done this on the exam. You would have just used the constants, right? So let's divide by the highest order of the polynomial in the denominator, which gives us 1 plus 2 zeta omega naught divided by s plus. All right. So right away we can see that we've got two integrators. These would be the A constants, right? And that there's only a constant up here, which really would mean that we've got B naught, right? 1 plus A1 divided by S plus A2 S squared. Now, I'm going into this level of detail because we're about to get into it, right? We're about to use that. But you could have drawn out the equation, divided through by the proper term, gotten this, and then gone straight to the picture, all right? And what I do is I have, for my solutions, I have a generic DF2 already done with all the constants and all the summers, and then I just delete everything. Now B naught is equal to 1. Now in the homework solutions, which I'll post, I really did it. I found the R's and the C's. Okay, because sometimes when you're doing a solution, you really need to verify what's going on, right? And at home, yeah, I would suggest you verify things. But basically, there's two integrators, and I always draw the integrators first. I draw them the same way every time so that I minimize my mistakes, right? Then, yeah, I'll put the summer here, and I'll add in the feedback. Now, this time I called it X and Y, so I would just call that Rx, R feedback 2, R feedback 1. You didn't have to label everything. I was really just looking for the structure. You might want to draw it like this. I don't normally draw it like this, but when you take one of the feedbacks back, to make sure you don't accidentally go into this node, if you draw it just like the positive summing node, right, it might actually make it easier. So this is the summer, right? the gain is 1, so in fact, this is the output. Now, if you put in a non-inverting summer, that's okay, right? If you put in a resistor and called it B naught, that's okay, right? If you put in an inverting one, well, no, that's not okay. And if you didn't label it, that's not okay. And if you labeled it on the wrong node, that's not okay. All right. So one integrator, but it comes out minus. We want minus, right? So we keep it that way. And I just labeled it, you know, you can label it RA1 or just A1. When I'm doing my schematics, I do that. Now here, now we have our double integrator and it's positive, but we wanted it negative, so we have to invert it. And see how if I draw it like that, you might make less mistakes. Now at this point, you can put a dummy, because the thing is depending on the values of R and C, right, you can get away with not having a dummy. You can do this, you can do that, or that is the dummy, right, actually. But I found it easier just to put 2 resistors of the same value because the gains didn't add up right. Anyway, how to calculate these? I did a 5th order Butterworth low pass example. There's a video, there's notes when you're working on your project. You know, I came up with what I think was a pretty straightforward way to make sure you get it on the first time. Now, you know, would you label this A2 and label that A1? Well, I don't, because they could also be B1 and B2, right, Artem? Wait, I'm sorry. Can you repeat it? Yeah. Hold on a second. RF1 is what? There is no A naught. All right. It just doesn't exist. In a sense, it's just part of it. And it comes from V out equals blah, 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 blah. So when I have V out 1 plus everything, there's the 1. There is no A naught. I'm only making a big stink about it because I saw it a few times. I didn't think you did that though. Anyway, doesn't exist. Okay. Now, yeah, I know you're under pressure. Now, sure, you can draw it like that, but some people forgot to connect that up. Some people did it backwards. This is a derivation circuit. It takes the derivative of over time. Okay. And I really think everybody can get 100% on this. Even the mistakes that I saw, I bet the next time around you can get it. All right. Now on the quiz, right, this was V out because it was the low pass. This node here is actually the band pass node, right? And if I take this and put it on and sum it into a summer, well, those would be the B constants and there would be the notch filter. This filter, right, this configuration, they actually use for a 3rd order circuit in those app notes that I showed. But if you can do this, you know, you can do just about anything, I'd say. Now, of course, in the solution, I show the Bode plot and all this stuff. You don't have to do that. All right. Any questions so far? All right. Now this one, we have a mass, right? We have a damper. It's fixed surface. And we have a moving surface. All right. Well, the input voltage is the input velocity. Goes through the inductor, or the spring, which is now an inductor. All right. The mass, one end of the mass is always tied to ground because the velocity of that mass is always measured with respect to ground. There's other ones where you might look at something different, right? But in this particular model, that's just always the case. Then the damper, one end is connected to one side of the mass and the other one is in fact. All right. Now, here's the thing. If I find the natural response, right, that means I'm really finding this, which is really this, which is really the parallel. And there's just this, you might by now know, just have this memorized because you have done it so much, right? And this kind of characteristic equation, if I find the roots, I can get my over-under critical. All right. Just tells you that. But really, we have our voltage division. ZC in parallel with ZR. ZL plus ZC in parallel with ZR. And really, if you made it here, in general, you got this. Oops. And here's the thing. These filters are always low-pass filters, right? It can't be anything else because you're measuring the output voltage across a capacitor and that decreases with frequency, right? The impedance of a capacitor decreases with frequency. So even though in this case it's in parallel with an R, when that capacitor gets smaller than that R, it's just going to be the impedance of the capacitor. And yeah, 1 over LC is omega naught squared. 1 over RC would be 2 omega naught S. S squared is the same. And 1 over LC is omega naught squared. So when I'm checking my work, I try to get it back into that form. Now, I was really particular about saying you got to get it into the right polynomial format, right? That was part of the question. And, but really, here's the thing. If you put down the series circuit, or maybe you swap those, it was wrong, right? You got to have the right circuit. Otherwise, problem doesn't make any sense. All right. Again, most people did pretty well on that one. The solution, yeah, I show all the mathematical spots. Okay. Now let's go to the buffer circuit. All right. And we're using the control system methodology. So in this case, we have the transfer function of the op-amp, the feedback parameter, and again, the transfer function of the op-amp. All right. The transfer function of the op-amp is the simplest frequency model, 2 pi gain bandwidth, which you would get off the data sheet divided by S. GS, in this case, is just 1. Now, maybe there could be resistors there. Maybe I could put a capacitor, resistor, inductor network, right? You can even put another op-amp circuit in the feedback loop, all right? So, two pi gain bandwidth, right? Divided by S, 1 plus So, when the magnitude of S is much less than 2 pi gain bandwidth, right? The whole thing goes to 1, right? It's a buffer. So, what frequency would that be? Well, the magnitude of S equals the magnitude of j omega, right, equals omega, right? So now we have when omega is much less than 2 pi gain bandwidth. Well, frequency equals omega divided by 2 pi. So the frequency would be much less than the gain bandwidth. Now, so that was about, I think, 10 kilohertz. But it actually doesn't have to be much. It seems to be pretty good when it's just F less than gain bandwidth. So 100 kilohertz. But if you were kind of being intuitive, you could have said, oh, you know, F is less than 1 megahertz, and I would have accepted it. You know, full credit. But F equals 1 megahertz is in fact the minus 3 dB point, right? So that it's near there, but no, it's not equal to it. It's something less. And you could have put this, you could have put that, you could have kind of left it at this. Now, some other issues, I didn't make a big deal out of it, but mixing radians per second and hertz, that's not a good idea. And then sometimes I would, because yeah, if you said omega is less than 2 pi gain bandwidth, okay, I didn't say in hertz, so this would have been okay. But there's this thing, I kept seeing a minus sign. Now, I'm like, well, is that just a dash? You know, people are in a hurry, but I saw it quite a bit. And I don't know, I'm not going to be able to ignore that next time. Now, it's true, this isn't a Bode plot. If I have omega radians per second and I have a low pass filter, yeah, right, there's minus omega and plus omega. The J's are there, we just ignore it, right? But if you had negative frequency, right, this would be the region that it would work, or here. But really, you can't test negative frequency. So it's really this part. It's gotta, I just don't know where that's coming from. I'm thinking there's a problem with the J. All right. I'm not gonna be able to ignore that next time. All right. This time I just chucked it off to, you know, an action, like some kind of mark that had no meaning. Any questions on that? Okay. Now, a lot of times we talk about the quadratic equation, and that's pretty good for second order. But really, when you get up to higher order, I think Descartes' rule, and yeah, I looked it up, or I think there's an ES. Anyway, it's Descartes. You know, you can say it with a French accent if you want, but and really, it's all about the sign changes. Now, this was in, I think, when I went and did the perpendicular, the inverted pendulum, I talked about it. It wasn't really in the notes, but if you take a polynomial, right, and we can just say s cubed plus 2s squared plus 3s plus 4, right? There's some things like missing factors. So if I had s cubed and I didn't have the s squared, or I didn't have the s, or I didn't have the constant, there's going to be a positive root, and it'll be unstable. There's another one where just put in -1 for s, or no, 1 for s. So you would have 1 cubed plus 2 1 squared plus 3 times 1 plus 4, and then count the sign changes. No sign changes, no positive roots. All right. Now, what that can mean is, what if I have, you know, this is minus, this is minus, and that is minus. I need something to change this to minus as well. Then there's no sign changes. All right. But with the right feedback, right, by looking at this term, right, if one is missing, put in a feedback that adds it in. If one is negative, put in a feedback where you can turn it positive. And then if there's sign changes, yeah, you can just remember you can do something with this and make, so if these are all negative, you can make this one negative too and it'll work. Okay. But a lot of times that's why I always try to get, I'll do whatever it takes with the rest of the equation to get the highest order of S to be positive. Because then I don't have to worry about other, I can see right away what sign changes I have to do. Now, that's, most of you just said with the quadratic equation, so we had minus 10, minus 10 squared minus 4 times 1 minus 100 divided by 2. Well, that's going to be positive, right? And then here, yeah, this is going to be positive. So while one might subtract it to where it's negative, we're going to add. There's going to be positive roots, okay? There's no way around it. So we have to fix it. Now, yeah, you could look at this equation and say, where'd it go? Oh, I'm going to need, so if I just looked at this, oh, I need to make this, nothing's missing, S squared, S to the 0. All right, negative, negative, and this is positive. I need to make this positive, I need to make this negative, and I could just say, oh, well, I need a K something S that will manipulate this to make it positive, right? And then I need a K something to manipulate this to make it positive. So that proportional plus derivative, right, should work just from that. And it does seem to be an easier way to do it than looking at the quadratic equation. But anyway, I think most people got that. I believe, oh, I don't have to believe, I can just look at it. So at the end of the day, K2 just had to be bigger than a tenth, and K1 just had to be bigger than 1. Now, just something interesting, right? If I have 2 poles here, right, I'm unstable, right? It'll be sinusoid. So what if I put what if after doing it, right, I have 2 poles here, right? Now you might, the way I normally draw things, I'd usually call that 1. But what if this is really minus 0.001, meaning I'm really zoomed in, right? I mean, it'll be underdamped, so it'll oscillate a lot, right? But if there's variances in my Ks, I might actually go unstable. To really make it stable, you probably have to bring it out more, right? And I think that's more like what 132 is about. You'll get an idea for that. And of course, maybe you want to make it, if you don't want any ringing, it's more than just making it stable, you make it critically damped. All right. But and they have a whole series of analysis techniques to talk about that kind of stability thing. Now, also, I think So stability in physical systems, yeah, it's that, you know, all reals less than 0, right? But I think sometimes in circuits, right, if it oscillates, they call it, it's like a shorthand, like very underdamped, right? Sometimes they might call that unstable. So just be careful, all right? But that whole thing with the op amps, right, where you can have, you know, just a simple non-inverting op amp, and you can have HS, right, you have some DC gain, right, that way you can put this into a feedback network and make the real term such that it will oscillate. I can't go into it today, but the term is phase margin, and you might want to look that up before some interviews, just as an aside. All right. Oh, that was it. Okay, FFT. Sine 2 pi 10 t plus sine 2 pi 20t, right? Well, this one's pretty straightforward. It's just a linear summation, right? So I have a sine added to another sine. Now, it might look a little funky on the scope, but really you have something with an amplitude of 1 at 10 hertz, something with an amplitude of 1 at 20 hertz. Now, this one, it might have tricked you for a little bit anyway. All right, so sine 2 pi 10t times sine 2 pi 10t is really what? Sine 2 pi 10 t squared, right? Which is the absolute value of that, right? So it, you know, I'm terrible at this, but notice the frequency doubles and there's a DC offset. So that's really, we actually get in this particular example, something at 0.5 at 0, and we get another 0.5 at 20 hertz because the frequency doubled. Because we really took, the period used to be this, but now when you take the absolute value, just like a full wave rectifier diode circuit, right? Okay. Sine 2 pi 10 t. Well, that's just if the Fourier transform coefficients are just the coefficients times sines and cosines, and there's only one sine with a coefficient of 1, well, That's that. Okay. If I have the same thing, right, plus 1, well, I have this, right? And I now have that DC offset, which is kind of what we're trying to do, right? This is a sine wave, okay? This is a sine wave plus 1, right? We're trying to get rid of, in our project, if I just try to draw a filter around it, right? I want this, and I want to get rid of this, right? Get rid of the sine and get the DC part back, right? Now, yeah, we're not using sine waves for our project. We are doing pulse width modulated signals. So if we have a 10% duty cycle from 0 to 1, right? That coefficient, so that's the average energy of this, right? It's 0.1. So I should get 0.1 at 0 hertz, right? Then you're going to get something at the fundamental, and I'm not asking you to calculate this, but here's something interesting. When we're at 50%, we kind of get this one shape, but if I let T get really big, right, I'm going to get this Fourier transform, this sinc function, which is sine x divided by x. So it's really hard to see at 50%, but at 10%, if I take out enough points, you'll see it kind of doing the sinc function. I just thought that was interesting. Now, yeah, you probably looked at it and said, well, which one's the sine wave? Then take that one out. Then, hey, which one is just adding 2 different sine waves? And then did that. What's the one with a lot of coefficients? Well, that's probably the pulse width one, right? A sine, and then maybe you looked at the sine wave with a DC offset, and then maybe yeah, the one where it was sine squared was the only one left, right? But that's pretty much it. Any questions? What? To the what? Quickly scroll up to what? Number 1? I mean, I'm recording. I'm recording. I have these, nicely written, and I just haven't posted it yet. So you'll have it. Okay. Now maybe what's missing is saying, hey, here's this second order structure, and the only difference is in fact the numerator, where you can be, the band low and high are just really, band is S omega naught, low is omega naught, high is S squared, and then the notch is the sum of these two. All right. Which really helps me to understand what's going on. We have some time. I can give back some more exams. I imagine I've made some addition errors or anything. Does anybody at home or not here have a question? You can just raise your hand or. Yes. Okay. I'll take a look at the due date of homework 11. My numbering thing really just screwed it up, and now I'm having to do it by hand. Unfortunately, when you know, it's my problem, but when you copy things over, it totally messes the due dates up. Okay. Alrighty,